Hi everyone, I'm Arthi. I'll be presenting our work on saturation throughput analysis of UORA-enabled multilink operation in IEEE 802.11be Wi-Fi. This work was recently presented in IEEE ICC Conference 2026. First, let's look at the evolution of Wi-Fi and the features in the recent Wi-Fi standards. Wi-Fi connects billions of devices worldwide and is the preferred choice of internet access. We use Wi-Fi everywhere in homes, enterprises, and also in public spaces. A significant portion of cellular traffic has been offloaded to Wi-Fi. To meet these demands, Wi-Fi has evolved significantly. And this figure shows the recent Wi-Fi evolution in the past decade. Starting from Wi-Fi 5, 6, and 7, we can see the peak data rate of Wi-Fi has improved from 6.9 Gbps to more than 30 Gbps. And a lot of new features has been introduced in each standard. And the key features introduced in each standard are mentioned here, which are multi-user MIMO, OFDMA-based random access, and multi-link operation. Next, let's look at the key features in detail in Wi-Fi 7 standard, which are uplink OFDMA random access and multi-link operation. In uplink OFDMA random access, the entire channel bandwidth is divided into multiple resource units. And the multiple users can transmit simultaneously over these resource units. So this OFDMA-based transmission supports concurrent uplink transmissions in Wi-Fi. And also, the access point controls this OFDMA transmissions by transmitting the trigger frames. And the users simultaneously transmit their uplink data through the multiple resource units, and then the access point acknowledges this transmission by transmitting a block acknowledgement frame. And this uplink OFDMA random access improves latency and also increases throughput. And the another key feature in Wi-Fi 7 is multi-link operation, which supports device can transmit and receive over multiple radio links. As shown in this figure, a Wi-Fi device can transmit over 2.4, 5 and 6 GHz radio links simultaneously. This multi-link also enables higher throughput and lower latency. In this work, we model multi-link operation with uplink OFDMA random access. In particular, we consider non-simultaneous multi-link which supports transmit and receive. It avoids more sophisticated hardware because the other type of MLO, which is simultaneous multi-link, which needs more sophisticated hardware because it needs to have sufficient power suppression across links. In multi-link, a device, since it can transmit over multiple links, it maintains backup mechanisms or backup counters for each link. The literature had explored two possible backup schemes for non-simultaneous multi-link operation, in which a device transmits on both the links based on the two backup rules which are mentioned here, which are the shortest backup rule and the longest backup rules. Since the user maintains backup counter on both the rules, in each of the rules, the access mechanism differs and follows a specific rule. In shortest backup rule, a device transmits on both links simultaneously even if one of the links counter reaches 0. However, in the longest backup rule, a device transmits only if both the links counters reaches 0. We show two links example in this figure, and there are 6 users transmitting on 2 links. And in the longest backup rule, since a user can transmit only if both links counter reaches 0, we can see the users 2 and 6 counters reach 0 on both links. Hence, in the longest backup rule, which is the second figure, users 2 and 6 simultaneously transmit on both links. However, in the shortest backup rule, a user can transmit even if one of the links counter reaches 0. So, along with users 2 and 6, users 1 and 4 also transmits. So altogether, users 1, 2, 4, and 6 transmit in the shortest backup rule. And when the users transmit in any backup rule, they randomly choose one of the resource units available and they transmit their data packet in the resource unit. Since it's randomly chosen RU transmissions, there can be success and collision events, which are shown in this figure. And the RUs also might be left idle. And the access point acknowledges the transmissions by transmitting a block acknowledgement in each link. And our contributions in this work is to characterize the joint evolution of backup processes of two links and analyze the throughput of non-simultaneous multi-link with uplink OFDMA random access. Now, let's look at the analytical approach of backup processes and throughput of this model. As we have seen already, the attempt and collision processes of the users are coupled because of the two reasons. One is the attempt processes are coupled because of the multi-link backup rules that we saw as shortest and longest backup rules. And after every collision, each collided user doubles its contention window. So if we model this backup process exactly using a discrete time Markov chain, the number of states in the discrete time Markov chain grows exponentially as the number of users in the system. Hence, we employ decoupling approximations which are conventionally used in the Wi-Fi literature starting from 2000. With this, now let's look at the backup analysis of the shortest backup rule. In the shortest backup rule, we can characterize the backup processes of a user using this state which is mentioned as S1 of t, S2 of t, and C min of t, where S underscore L of t is the backup stage of link L of a user and C min of t is the minimum backup duration of a user. In the shortest backup rule, minimum backup duration is sufficient to track because a user attempts if one of the links counted becomes 0. I note that it is not minimum backup counter, but it is the duration in T of cycles because here the backup counters are decremented by number of resource units in uplink OFDMA random access. Now let's look at this Markov chain closely, where S1 of t and S2 of t, which are links backup stages, which they can take values from 0 to rho, where rho is the maximum backup stage in any link. And the minimum backup duration can again vary from 1 to till some number which is given here, which is u, and it's again a function of backup stages of each link. For more details and distributions of this backup duration, please check the paper. Now let's look at the evolution from a state which is 0, 0, 1, where the backup stages are 0 for any link 1 and 2, and the backup duration is 1. And the backup duration is 1. It is the last TF cycle, and in that TF cycle, after the access point transmits the trigger frame, and the users decrement their backup counters by the number of random access RUs, and in that trigger frame cycle itself, the users transmit. That is the reason from 0, 0, 1, the users transmit on both the links simultaneously. Because there are two links, there can be 4 possible events because it can be a success on both links, collision on both links, and success on one link and collision on the other. And the transition probabilities captures all these 4 events here. And again, like conventional Wi-Fi DCF transmissions, after every collision, the backup stage is incremented by 1. And if it is a success, the backup stage is reset to 0. And the counter values are chosen uniformly from a window, and the backup durations again will be uniformly chosen from the given duration. And we calculate the steady state probabilities of this Markov chain numerically, and the attempt probability of a user under this backup rule is given by this expression, where the backup stages of a link is summed over 0 to rho, and the TF cycle has to be 1. Similarly, we can also characterize the collision probability of a user in uplink OFDMA random access. And again, it depends on a link because the collisions on a link depends on the collision processes happened or collision events that happen in that link, and the user collides if any other user transmits on the same random access RU. So gamma L, which is the collision probability of a user in link L, is given by this expression. I noted here the gamma L depends on the number of resource units, which is n underscore L on link L. Now, since we have the probabilities of attempts and collisions, we can characterize the saturation throughput of a user in non-simultaneous multilink with uplink OFDMA random access, which is given in the green color box here, which is theta underscore L, which is the throughput of multilink on link L. Here, T underscore P and TH are the duration of payload and the TF cycle. And here the throughput is a function of total number of users and the attempt probability and the collision probability. And RL is nothing but the average rate of a user with rate adaptation. In our work, the user's rate are adapted because they are in different distances from the access point, and we also model small scale Rayleigh fading. And depending on the varying SNR, the user's rates are adapted, and we choose one of the available MCSs given in the Wi-Fi 7 standard. So the average root rate of a user is averaged across the MCSs given in the Wi-Fi 7 standard and also the different distances of the user. With this, now let's look at the throughput of this model where we plot the throughput of multilink with uplink OFDMA random access. In this figures, we plot saturation throughput of non-simultaneous multilink with uplink OFDMA random access for two different RU configurations, where there are 8 RUs on link 1 and 4 RUs on link 2, and the number of RUs are same on both the links. In both the figures, we can see the black curves are for the multi-link throughput, and multi-link throughput is definitely higher than the single link throughput, which are shown here in the red and blue colors. And the throughput numbers of multi-link depends on the backup rules, which are shortest and longest backup rule. And in the shortest backup rule, the throughput increases first as the number of users increases, which is seen nicely in the second figure because the number of successful transmissions increases. However, for more number of users, the throughput decreases than the longest backup rule. That is because the shortest backup rule is aggressive and the users transmit even if one of the counters reaches 0. So when the number of users are more, all the users attempt aggressively, which increases the attempt probability and also the collision probability. However, in the longest backup rule, the throughput is lower because the users wait for both the counters backup counter reaches 0, and it increases as the number of users increases. And these plots are for a given bandwidth, which is 160 megahertz bandwidth on both the links, and the payload duration is 5 milliseconds, and the minimum and maximum contention window values are 16 and 1024. And as I already said, the users are distributed around the AP with a minimum duration, with a minimum distance of 1 meter and a maximum distance of 50 meters. Now, the second figure validates the reasoning that we mentioned for the throughput in the first figure. Because I said in the shortest backup rule, the attempt probability of the users are higher, right? We can see the attempt probability of the users are always higher for the shortest backup rule for the same reason, because the users attempt even if one of the counters reach 0 in the shortest backup rule. The same reason, it also has higher collision probability, and the longest backup rule's collision probability is lower than the shortest backup rule. And since from this expression, as we saw, the collision probability is a function of number of random access RUs, we can clearly see the gamma L, or the collision probability, depends on the number of RUs here, because we have 8 RUs on link 1 and 4 RUs on link 2, and we can see the second link has more collision probability because of the lesser number of RUs. And we have come to the conclusion or the key takeaways in this work. The key takeaways are the multi-link uplink OFDMA random access has a higher throughput than single link based uplink OFDMA random access, and the throughput gains depend on the number of random access RUs and the backup rule. And I'll also list down the possible extensions for this particular work, where we can also analyze the access delay of the multi-link with uplink OFDMA random access with and without legacy users. And in the presence of legacy users, the access point also needs to contend with the legacy users to transmit the trigger frames. And we can also look at the performance, throughput and delay performance with different traffic such as unsaturated traffic of legacy and Wi-Fi 7 users. Thank you.